Okay, on to simple interactions. Remember when we did simple effects tests, we looked at the effects of one factor over the level of each of the others. For a three-way interaction, what we're going to do is look at the effects of two of the factors isolated at each of the levels of the third factor. And generally with a between type design, it's probably best to isolate across the levels of the between subject factor. Uh, so we're going to look at time and condom interaction separately for lower, middle, and upper SES. So what we end up with are just three two-way within subject ANOVAs. If we have a three-way interaction, what that's telling us on the surface is that the two-way interaction patterns differ between our groups. How do they differ? Well, that's what the simple interactions tests are going to help us to describe. Here's the low SES, and you can see for the low SES, time by condom interaction is still significant. This suggests that for those kids who are from the lower SES backgrounds, that the program paired with the free condoms is most effective. For middle SES, we see no significant interaction. In fact, nothing was significant. What is this telling us? Well, it's telling us that something about the program is no good for these middle class kids. Something about the program isn't helping them. It isn't filling the needs, their needs. And then the upper class kids, here we see, okay, well, they do fine with just free condoms. We could just make sure that free condoms were available for these kids, and everything would be fine. They don't actually need the program. So you can see how these sort of results can really start to inform program development. Now here, you might think, okay, well, I'm going to focus this program on the low income kids because we know it works with them. And we're going to look for something different for the middle class and the upper SES kids. And again, this just gets down to breaking down those patterns that we saw. The different analyses just correspond directly to these graphs. All right, how do we do this with linear mixed models? Linear mixed models, it gets a little bit more difficult. The reason being is that we have to do this in steps. So you can see I've built all of the different models, and I've built them, a variable or an effect, I should say, at a time. And then finally, we get the likelihood ratio at the end. These usually come out looking pretty much like the F test. So we can see we still have a significant three-way interaction, lots of significant stuff underneath that as well. So really same approach here. Nothing really different. We just have to specify the different values and then what's within subject in the ID/time/condom piece. And if we want effect sizes for linear mixed models, people often think that linear mixed models are somehow deficient because you don't automatically get a measure of effect size. You can actually tweak it to get a measure of effect size. So I played with this a little bit. And what I found is using a different package, one called LME4, which has a command that I really like called lemur, because lemurs are cute animals. I ran this analysis. Here I'm just going to show it with two factors. So risk, time by condom. You see the format is a little bit different here. We don't have the tilde one. We have one full slash rather than backslash ID, and then the name of the data set. So a pretty similar type thing. You can see this will run an analysis. It'll give you things in terms of a t-value. But we can do a command called sorry. So my summary here has estimates and standard errors, and what I've done here is I am going to issue the command ANOVA on the object that holds my analysis, which is called fit, and that's going to give me a table here. It's going to give me some table of some ANOVA values. Well, what do I do with these? Well, I can use those sums of square values to get at the partial eta squared or the regular eta squared. The only issue here is we don't have the within subjects value. However, we can get the within subjects value. I know that the F value for any of these is going to be the mean square for that effect divided by the mean square within, or the mean square error, I should say here. The mean square error, how can I find the mean square error? Well, it's just a math problem now. I just need to solve for that. So f value is going to be equal to the mean square over the unknown mean square. So it just becomes a little bit of a rearrangement problem. Here's a little bit on using objects to do calculations. I mean, you can do calculations by hand, but if I'm sitting at a computer, I'm kind of loath to be doing calculations by hand. So the numbers in this table, in fact, this object is just holding a set of numbers. And we can specify different numbers using this format. YY, that's the name of the what I call the table. 1, 2. 1 means take the value in the first row and second column. And you can see I've highlighted that in red, times mean square value. Well, why are we doing that? Well, what I can do is I can get all the values I need for a calculation. I also need, say, if I wanted the F value for condom, YY2, second row, fifth column. If I wanted any of the other values, I could specify them the same way. Again, we don't have sums of square error, but we can get that mathematically. So first up, I calculated the mean square within. That's just the F value multiplied by, that's the mean square. I then calculate the sums of square within from it. And then the partial eta squares are just the sums of squares for our effect, divided by those effects plus the sums of square within. So very easy to get each of these. I got partial eta squared and regular eta squared here, so we can use either one. Of course, I don't know why they're in this order. Yeah, I see why they're in this order. One thing to note is that eta squared is always going to be smaller than partial eta squared, of course, because of how it's calculated. Come on. Sorry, my controls keep disappearing.